Good evening. This is week 6 of applied thermodynamics problem solving session. Sorry, week 5. And we saw in the previous week we finished on the Rankine cycle. We saw the components of the Rankine cycle, did an exergy balance of the Rankine cycle, and we saw where maximum loss is happening, how we can improve the efficiency of the Rankine cycle, and so on. So Rankine cycle was basically we started with the Carnot cycle, so which is the basic cycle which will give you a maximum efficiency. So as the Carnot cycle had practical difficulties, which we saw, so we tweaked or changed some of the Carnot cycle process, and we got a Rankine cycle. So this happened inside a two-phase dome, because we cannot have a constant temperature process anywhere else. So we went inside a two-phase dome for a pure fluid which will have a constant temperature. So you can change that constant temperature into constant pressure process. So we will still get some region which is at constant temperature. So that was the idea, and we went from Carnot cycle to a Rankine cycle. So now moving ahead, we will see gas powered cycles. So this week will be on internal combustion engines. So to start with, any heat or any cycle can be classified as two. One is power producing or power absorbing. So in power absorbing you have compressor or heat pumps. So in power producing, if you see, you have internal combustion engines, you have air motors and external combustion engines. So internal combustion engines again is reciprocating type and rotary type, and so on. Similarly, in external combustion you have reciprocating and rotary type. So that which can be again classified based on how the flow is happening and so on. So in reciprocating type and internal combustion engines, which we will be looking at this week, so we have spark ignition and compression ignition. So spark ignition is we know normally we see petrol bike engines, you have spark ignition, and compression ignition you have diesel engines or oil engines, and there is again gas engines. So this again engines, then you have air cooled or water cooled. So bigger engines you cannot have air cooled, so you go with water cooled. But normal what we have in roads, let it be bike or cars, we have air cooled engines. So these engines can operate two ways. One is two stroke and other is a four stroke. So that's one. So in the rotary type, if you see, you have power producing, you have steam turbines, so radial flow turbines or axial flow turbine, which we saw in the previous week Rankine cycle. And then the types of turbines which we also saw. So just to put a idea of how it's classified. So then moving on. So what is the advantage of having a reciprocating internal combustion engine? And so this is a comparison between internal combustion engine and external combustion engine. So what is external combustion? You are having a combustion outside where you're producing heat and you're transferring it to the fluid and you're getting out of work out of. Internal combustion engines, everything is happening inside. So what is the advantage? So reciprocating internal combustion engine has overall efficiency is high. So it has mechanical simplicity, and your weight to power ratio is low, and generally it has lower initial cost and easy starting from cold condition. So this your internal combustion engines are compact and it will have less space requirement. So these are some of the advantages of the internal combustion engine. Then what is the advantage? We'll also compare both. So what is the advantage of having an external combustion engine? So external combustion engine, your starting torque is very high. So because of external combustion of fuel, cheaper fuels can also be used. So even solid fuels can be used. So that's going back to using coal and generating steam and so on. So that can be used advantageously. Due to external combustion of fuel, it is possible to have flexibility in arrangement. and these units are self-starting with the working fluid, whereas in case of internal combustion, some additional equipment or device is used to start the engine. So this is how an internal combustion engine looks. So we'll see how each part, and we'll try to understand what happens. So compare this with your a bike, so where your engine is visible. So this is the top portion. You can see small sheet kind of thing which you can see outside. So those are the fins, cooling fins. So inside this sits a cylinder where you have a piston assembly. This piston moves up and down in the cylinder, compressing the fluid and expanding. And on top of this cylinder, you have a cylinder head. So this cylinder head contains the ports or valves. So you have an inlet valve and you have an exhaust valve. So with this valve, you have spring arrangement to bring it back on, push that, so on. And usually in cars, you also have a camshaft which will time the opening based on the rotation of the crankshaft. So that will push the valves to have inlet opening or the exhaust opening. So there will be camshaft above that, and then you have the piston. So piston, the top is, will be a similar different shape based on your requirement. So I'll come that camshaft is basically drives your valves. It just opens the valves and close. So here in crankshaft, what happens is that is connected to the piston. So that transmits the power. So that's the crankshaft, and camshaft is just to time the openings of the valve. So you have similar valves with a profile with different profiles. So like an eccentric, create an eccentric one. So you have different profiles in the shaft, which will sit over this ports, valves, and which will just push the valves down. So that's camshaft, and crankshaft is you have piston, so which is connected through a connecting rod. So connecting rod, and then the connecting rod is connected to the crankshaft. So whatever power is generated is in turn rotates the crankshaft, and you have the power delivered. So this piston, as I tell, piston may have different types of top. Can have different variation profiles in the top. So that is there, and then this piston is connected with the connecting rod using a pin, and then this connecting rod is connected to the crankshaft, and this crankshaft generally will also have oils in there to cool the overall inside and lubricate. So this is how internal combustion engine looks, and these fins which are generated is again, this is an air cooled internal combustion engine. So when the vehicle is moving, you have air which is coming out. You use that air, the high velocity air which is coming to cool the engine. In case of an water cooled internal combustion engine, you will have openings or jackets, you can say, in the internal combustion engine, where through which you will pass water to cool the engine. So some of the terms and how the engines are denoted. So if we have stroke is just how much the piston moves. So from top dead center to bottom dead center, so that is called as stroke, or just the length, how much length the piston travels. So that is called as stroke. And the clearance volume is generally if the piston is at the top position, so it cannot move any further. So that and the cylinder head, so how much volume is occupied, so that is called as clearance volume. So you basically require clearance volume because you have valves, and so you need space for those opening, and you also need some clearance. So or else the piston will go hit the head. So you don't want that happening. So you require that clearance volume. So that is called as clearance volume, and the inlet is called as inlet manifold and exhaust, and bore is your cylinder diameter. So cylinder diameter is termed as bore, and the length which the piston traverses is called as stroke. So using this, engine is defined as if your bore diameter is less than the length, it's called as under square engine. If it is equal, it's called as a square engine, and if it is greater than L, it's called as an over square engine. Is this terminologies? And then the compression ratio. So compression ratio is called as the total volume divided by the clearance volume. So you can write it as 1 plus Bs is swept volume. Swept volume is the volume swept by the piston cylinder. So that is your area of cross section into the stroke. That will be your swept volume. So divide by the clearance volume. So that will give you the compression ratio. And then so ideally your thermal efficiency will be your input power divided by Q. Q is the heat which you are generating, and then BP is the brake power, or because you have some frictions and so on. So taking that into account, you have lesser power which you are getting out. So that is brake power divide will give you the brake thermal efficiency, and then combustion efficiency is your heat divided by the total calorific value of the fuel. So say again, the mechanical efficiency will give you the ratio, so you can know how much fraction is lost in friction. So again, and then volumetric efficiency is a mass of air divided by rho into V into density. Rho into V. So V is the Vd is the displacement volume, or you can say a swept volume. So rho into swept volume. So now we saw that internal combustion engine can operate in two ways. That is, one is four stroke and another is two stroke. So now we don't usually see two stroke engines. What we are using all are four stroke engines. So how does a four stroke engine works? So it has again four processes. So stroke is, as I told, in which the piston traverses a length from top dead center to bottom dead center, or the other ways. So in four stroke it traverses 4 times. So each traveling is a process. So first you have a suction stroke. So in case of a suction stroke, what happens is your inlet valve is open. So and your piston comes from the top position to a bottom position. So now there is a vacuum which is created. So in this case your valve will be opened and your air fuel mixture which will enter and fill the cylinder space. So that is a suction stroke, and then there is a compression which will happen. So whatever fuel and air mixture is taken, now the piston will start moving from bottom position to top position. So the fuel and air mixture which is there, it will get compressed. So once it reaches some position, so your spark plug will be ignited and the fuel will start combusting. So from there, due to the combustion process, the gas fuel will the pressure will increase and it will start pushing the piston down. So this is what is the main process which gives you work. So after this, when the piston reaches down, it will start moving up again. Now your exhaust valve is open, and the gases which are there inside will start going out. So if you see, then again it will go back into cycle. From top position, it will start coming down, and inlet valve will be open, and it will go in a cycle. If you see in a two-stroke engine, So in case of 4-stroke engine, what happens is okay, so here I think no, it's I think the diagram there is a confusion because no, it's correct. So everything is it goes in anti-clockwise. Here, as per the diagram, it all is in anti-clockwise direction. Okay, and yeah, in this, if you have a cycle completes in 2 revolution of a crankshaft. So 4 stroke in each revolution you have 2 strokes. So one coming from top to bottom and bottom to top. So this happens in 1 revolution, and so you have 4 strokes for a process to complete, a cyclic process to complete. So you require 2 revolutions. So generally what happens is the only work generating one is your working stroke. Rest others has to be work has to be driven by this working stroke. So you generally have a flywheel which stores a part of energy which is used in the rest of the processes, and the net work which you are getting, that is what you get outside from the engine, which you use it in driving the car or any other process or generating electricity or so on. So in case of a 2-stroke engine, so in this case these are not generally used now. So you have in this case exhaust port at near the cylinder and inlet port near the crankshaft, the sump. So what happens here is when the piston moves down, the inlet valve here is open, and you have gas which comes and fills the crankcase, and the piston here compresses that crankcase, and you have an opening. So you have in the left position you have the exhaust and the inlet port, and in the right you will have a port which connects the crankcase to the cylinder. So when the piston moves down, at the top there will be opening which is now open. So the exhaust gas would have all left, and the inlet gas would go back and fill the cylinder, and then the piston will start moving up. It will compress, and there will be a spark plug, and now there is a combustion, and it will start pushing the cylinder down. So what happened is, whatever happened in 2 revolution, now in 2-stroke engine it happens in a single revolution. So the working stroke and the compression stroke are combined, and your inlet valve coming in and your exhaust going are also combined. So those 4 processes are combined into 2 in a 2-stroke engine. So in this case you have a continuous power generation in each revolution. So in a 4-stroke engine you had a 2 revolution which provided 1 working stroke, but in 2-stroke engines you have each revolution providing a working stroke. So to compare the two 4-stroke and 2-stroke engines, so the cycle is completed in 4 strokes of the piston, as I told, or in 2 revolution. And in cycle 2-stroke engine you have 2 strokes, and 1 revolution the cycle is completed. So the flywheel required heavier or lighter. So because of above turning movement, as I told, the flywheel is one which stores energy and is used in the rest of the process. So you require heavier flywheel in 4-stroke engine compared to a 2-stroke engine, because in each revolution you are generating power. So the power required is smaller in a 2-stroke engine. So power produced for same size. So because 1 power stroke for 2 revolution, power produced for smaller size engine is small, or for the same power the engine is heavy or bulky. So in 2-stroke engine you are getting more power, or the engine size is smaller. And cooling and lubrication requirement, because of 1 power stroke in 2 revolution, lesser cooling or lubrication requirement. Here you require higher lubrication and cooling requirement. So valve mechanism, 4-stroke engine contains valve and valve mechanism. So valve mechanism is the camshaft in which I talked about. So 2-stroke engine have no valves but only ports. So port is just that opening so that is closed by the cylinder and so on. So that will take care. So you don't require a separate valve mechanism for a 2-stroke engine. And in 4-stroke engine, the initial cost will be higher because it's bulky or heavier compared to a 2-stroke engine, and it requires separate valve mechanism and so on. And volumetric efficiency wise, volumetric efficiency is more due to more time of induction. Here in this case, volumetric efficiency will be lower. So what happens basically, if you think, so here when the exhaust valve is open and the gas goes out and inlet valve is coming again, before all the exhaust gas has gone out, your inlet air and fuel mixture has started coming in. So that will push some of the exhaust gases, but still most of the gases is mixed with the exhaust gases. So your effective mixture, air and fuel mixture, which has not participated in combustion, is very less compared to a 4-stroke engine. So hence the volumetric efficiency in a 2-stroke IC engine will be lower. So thermal and part load efficiency. So thermal efficiency will be higher and part load efficiency is better than a 2-stroke cycle engine. Thermal efficiency lower, and so your efficiency wise, your 2-stroke engine efficiency is lower.
Yes, sir.
Yes.
Sir, can you explain this four-stroke second point, sir?
Your flywheel, about the flywheel.
Yes, sir. Flywheel.
Yeah. So flywheel, what basically it does is, uh, so your power is just generated. So that
Yes,
power
sir.
is uh, so you see the cycle is continuously rotating. Your crankshaft is continuously rotating, but your power is getting generated only once out of 4 strokes, and your outlet requirement is a continuous requirement, right? So what happens is your power which is coming out is controlled by this flywheel. So that gives you the sudden change in whatever variation. So that will give you the power output, as well as that will it's like basically a storing device, mechanical storing device. So you can think it as battery or something. So you are charging it in the working cycle and discharging it in the other 3 cycles, and using that power to continue the cycle running. So that is higher requirement is there in a 4-stroke engine, because you have 1 stroke which is working stroke, but 3 strokes are power consuming strokes. So the flywheel size and requirement is higher in case of a 4-stroke engine compared to a 2-stroke engine. Is it clear?
Okay, but in the point, it's telling turning moment above the turning moment.
Yes. See, that's what in 4-stroke. If you have one revolution, you have 2 strokes. So in 2 revolutions, you are getting only 1 stroke, which are getting work output. In case
Yes,
of
sir.
2-stroke, each revolution you are getting one work output. So if you see in 4-stroke, one revolution there is no work output. In other revolution you are getting work output, and then there is no work output. Then there is again one work output. So it's kind of non-uniform, right?
Yes, sir. Right,
Once
sir.
you get, once you don't get, and once you get. So the requirement of flywheel is more to make you get the output which you get, where you have continuous requirements for movement. So there the flywheel takes care of that. In case of 2-stroke engine, each revolution you are getting work, so the flywheel requirement is smaller.
Right, sir.
Okay. And so the last point is on the thermal efficiency. So thermal efficiency in case of 4-stroke engine is higher compared to a 2-stroke engine. So moving with MCQs and some problems I've prepared at the end. So we'll start with some MCQ questions. So the process of injecting pressurized air in the cylinder is called as dash. So the answer is supercharging. So what exactly happens is there's a component called a supercharger or turbochargers in some. There's also a turbocharger. So what exactly happens is you put a small compressor kind of thing, or you in some cases in a turbocharger what happens is the exhaust which is there, you use it to drive the compressor, which basically compresses the inlet air which is coming in, and you pass on the pressurized air into the cylinder. So the inlet air is pressurized, so this basically is done to increase the efficiency of the system. So the process of injecting pressurized air in the engine cylinder is called as supercharging. The next question is the mean effective pressure measured from the engine indicator diagram shows the dash: A maximum pressure, B minimum pressure, C instantaneous pressure, and D average pressure. So any guess what it could be?
Sir, average.
It's average. So in this case, mean effective pressure. So mean in entire case way to write that is an average. So in the problem we will see how to calculate the mean effective pressure. So before I will show you how to calculate it. So for now, mean effective pressure is shown using average pressure for the engine indicator. Indicator diagram is nothing but the process shown in a PV diagram. The percentage of energy lost through exhaust in SI engine. So SI engine is a short form for spark ignition engine or a petrol engine, you can say, is higher than the CI engine. CI engine is a compression engine, compression ignition engine, or you can say diesel engine. So the percentage of energy lost through exhaust is higher in SI engine or a CI engine. So if they are saying SI engine is more than CI engine, so answer is true, because higher RPMs and SI engine has higher RPMs and it has higher combustion temperatures, so which leads to more energy being carried away by the exhaust gases. So answer is true. So higher RPMs means much more mass of energy, mass of fuel, mass of exhaust which is coming out compared to a CI engine, and because the temperature is also high, so the exhaust gases which are coming out are at higher temperature in a spark ignition engine compared to a compression ignition engine. So higher temperature means higher internal energy, so we have more energy which is taken away by the exhaust. So answer A is true. So next is an engine indicator diagram is used to determine dash: A speed, B mean effective pressure, C indicated horsepower, D both mean effective pressure and indicated horsepower. So in this case, if you see indicator diagram is, as I told you, is a process shown in a PV diagram. So mean effective pressure is your average pressure, so which we saw on the previous. So you can get mean effective pressure. The second is indicated horsepower is your work done, so actual theoretical work which you can get out of a process. So indicated horsepower can also be you can get from a PV diagram. So the area under the curve or area under the cycle enclosed by the cycle, so that gives you the work done. So you can get indicated horsepower. So answer is both mean effective pressure and indicated horsepower. So indicated horsepower is nothing but the work done, the total work you can get out of a cycle. So next is, if the intake air temperature is decreased, then the efficiency of engine will dash. A, increase, B, decrease, C, remains same, D, increase to a limit value and then decrease. So what do you think will happen? Can take a guess. You can write it in the chat box if you want. So answer is yeah, and I think this is a mistake, that it should decrease. If the intake air temperature is decreased, the efficiency of engine will decrease. So there's a mistake here. I'll correct it while uploading. The firing order in an IC engine depends upon dash, cylinder arrangement, crankshaft design, number of cylinder, and D, all of these. So firing order is in this case is because you have multiple cylinders, you are engine, so you would have heard term called V6 and so on, an engine V6 engine, and so that is basically how the cylinders of engines are assembled. So 6 is for example V6, it shows that it has 6 cylinders arranged in a V shape. So in V shape you have the cylinders which are placed, 6 cylinders in, so 3 and 3 in V shapes. So in what orders the engine has to be, spark plug has to be ignited, so that is what is been asked. So what is that depends upon. So A, cylinder arrangement, true, in how the cylinder is arranged, so it takes into account the firing which has to be done. So this multiple cylinder is also taken into it's also used because and the arrangement is also placed such that you get output, uniform output, to take into account of that. So because a single cylinder cannot give you that uniform output and higher torque and so on. So this arrangement also takes care of that. So A is true, and your crankshaft design is also is important in determining the firing order, and also number of cylinder. So in which cylinder has to be fired first, which has to be fired last, so on, all comes into play. So answer is all of this. So next is, mechanical efficiency increases with increase in dash. A, brake power, B, indicated power, C, friction power, and D, none of this. So we saw in the nomenclature. So mechanical efficiency is a function of brake power divided by friction power. So if your brake power is same and indicated power increases, so your efficiency decreases. Or if you say the friction power increases, friction power is difference between indicated power and brake power. So if that friction power increases, again your mechanical efficiency is decreasing. So if your brake power increases, that means you have lesser friction power. In that case, your mechanical efficiency will increase. So answer is A, brake power. So brake power is nothing but brake power equals indicated power minus friction power. So this all will come also in practicals, and they'll also teach you how to calculate engines friction power, indicator power, and so on. So how to estimate. So that also will come, but that's not covered in this course. I think I may have some numericals, but I'll see. So the number of that numericals will, they basically can calculate brake power and theoretically, but in practicals you will find how you can in what you have multiple cylinder engine, how you estimate an indicator power or a friction power of an actual engine. So in this case we will just from the problem we the simple equation we will use that, we will calculate the efficiency of engine and so on. So the next question is, the number of working strokes per minute for a two-stroke engine is dash the speed of the engine in RPM. So number of working strokes per minute they are asking. So for a two-stroke engine, so we know for two-stroke engine, for each revolution you have one working stroke. So answer is equal to, if it would have been a four-stroke engine, then that would be half of then speed of the engine. So if you have the speed of the engine is 1000 rpm, so that means you have 1000 strokes working strokes per minute. And if it would have been four-stroke engine and the engine is running at 1000 rpm, you would have 500 strokes per minute. So because in each rpm you have two strokes, and in two-stroke engine, out of two stroke, one is working stroke. So you have one working stroke per revolution of engine, and one stroke for two revolutions of engine in a four-stroke engine. So in this case problem, it is equal to. So moving on to next question. If W is the brake load, L is the length of arm, N is the speed of the engine, S is the spring balance reading, D is the brake drum diameter, and D is the rope diameter, then the relation of brake power of the engine can be expressed as. So to show you an arrangement how a brake power is brake load or is calculated. So you have a shaft with the pulley, and so you are mounting a rope around it, and there is a weight which is suspended. So and it is mounted on a spring balance. So this is how it looks. So if you see the spring balance will show you some reading, and you have some W. So if you balance it at the top, so the tension reading will be the spring reading. So the net force which is acting on the wheel will be W minus S. So W minus S into your radius. So that will be the wheel diameter plus the rope diameter, 2 times the rope diameter, divided by 2. And into number of rotations or the angular velocity, which is 2 pi n by 60. So n is the speed of the engine. So if you calculate it, it will become W minus S into pi into D plus D, this will be this from the center distance to the center of the outer rope. So it will be D plus D. It cannot be T plus 2D. So 2D will be the outer one, because here this will be acting at the center of the rope. It will be the wheel diameter plus smaller radius of the rope this side and that side. So it will be D, capital D, which is the wheel diameter plus the rope diameter. So the net force is W minus S into radius into omega, which is 2 pi n by 60. So that will come out to be option C, W minus S into pi D plus D into n by 60 watts. So any doubt here? Okay. So next question is, in general, the thermal efficiency of a two-stroke engine has a lesser value than a four-stroke engine. So this we have already seen in the classification. So the thermal efficiency of a two-stroke engine will be lesser. So answer is option A, true. So next is a four-cylinder two-stroke cycle diesel engine with 10.9 centimeter bore and 12.6 centimeter stroke produces 88 kilowatt of brake power at 2000 rpm, and the compression ratio is 18.1. Calculate the following. So we'll see some numericals now. So we have a four-cylinder two-stroke cycle diesel engine. So number of cylinders given is 4, and it is working in a two-stroke. So for each revolution you are having a working stroke. Now next is given is your diameter. The bore diameter is 10.9 centimeter and stroke is given as 12.6 centimeter. This engine is now producing 88 kilowatt of brake power, and the revolution is given as 2000 rpm. The speed of the engine is 2000 rpm, and compression ratio is also given, which is 18:1. So the compression ratio is 1 plus swept volume by clearance volume. So we need to calculate 1, engine displacement, 2, brake mean effective pressure, C, third is torque, and D, clearance volume of one cylinder. So we will see how to solve this. First is engine displacement. So engine displacement is nothing but your number of cylinder into pi by 4 into the diameter or bore square into stroke length. So this will come out to be 4 into pi by 4. So your bore is given as 10.9 centimeter. So 10.9 square into stroke is 12.6 centimeter, which is 4703 centimeter cube, or 1 centimeter cube is 10 power minus 6 liters. So 4.703 liter. So brake mean effective pressure, that will be your total work done divided by the swept volume and into number of rotations. So work is per stroke, so per stroke divided by Vd into speed of engine. So the brake mean effective pressure will be, so in the problem it is already given that the engine produces a brake power of 88 kilowatt. So 88 into 1000 divided by 4.703 into 2000 by 60. So that comes out to be 561 kilopascal. So that is the brake mean effective pressure, or you can say the average pressure. And third one is torque. So torque is T is brake pressure, brake power divided by 2 pi n. So because your power is T into omega, so omega is 2 pi n. So brake mean effective pressure into Vd divided by 2 pi. This is the other way of writing. So if you see, brake power divide by Vd into N is brake mean effective pressure. So you can just take the displacement volume to the other side. So you will get brake mean effective pressure into Vd by 2 pi. So that is torque. So substituting here, so your brake power is 88 kilowatt. So 88 into 1000 to convert it into watts, divide by 2 pi into N is 2000 by 60. So this comes out to be 420 Newton meter. Then the clearance volume of one cylinder is, so we know the displacement volume here. So the displacement volume of which we have found out is for the 4 cylinders. So because we have already multiplied with the number of cylinder, so for each cylinder we have to find out the clearance volume. So for that, compression ratio is known, so we need to substitute there the displacement volume of each cylinder. So displacement volume 4703 divided by 4 number of cylinder. So each cylinder will have 1176 centimeter cube of displacement volume. So the compression ratio is displacement volume plus clearance volume by displacement volume. This is 18. So your clearance volume will come out to be 69.2 centimeter cube. So any doubts here? Okay, so moving on to next question. A 4 cylinder 2.4 liter engine operates on a 4 stroke cycle at 3200 rpm. The compression ratio is 9.4:1. The connecting rod length R equals 18 centimeter, and the bore and stroke are related as S equals to 1.06 B. So this is an over square engine. So S is 1.06 B. So calculate the following: A, clearance volume of one cylinder; B, bore and stroke; C, average piston speed. So what is given, we'll break it down. So we have number of cylinder present in the engine is 4. So the total capacity of the engine is 2.4 liter, and it operates in a 4 stroke, and the speed of engine is also given, which is 3200 rpm, and compression ratio is 9.4:1. Then what is given is a connecting rod length is given, so that we will use in the piston speed calculation. So R is 18 centimeter, and then they have given you a relation with bore and stroke, saying that your stroke is 1.06 times of bore. So your clearance volume of one cylinder will be, so this is given as 2.4 liters. So your displacement volume, so total displacement, your capacity of engine is 2.4 liters. So your displacement volume for each cylinder will be 2.4 divided by 4, which comes out to be 0.6 liters or 600 centimeter cube. Now we know the compression ratio. So compression ratio is nothing but 1 plus clearance volume by displacement volume. So substituting that, this will be equal to 9.4. So we know displacement volume of each cylinder, and compression ratio is 9.4. So your clearance volume by displacement volume will be 8.4, and we know displacement volume is 600. I think I made a mistake in compression ratio. So this will be 1 by 9.4. So this, or you can say Vd by V. The bottom one B is not Vd, it's Vc. So in that case, it will come out to be correct. So it will be 600 by 9.4, which comes out to be 71.43 centimeter cube. So bore and stroke. So your displacement volume is known. So using that bore and stroke relation, we can estimate bore and stroke length. So your displacement volume is 600 centimeter cube. So which will be equal to pi by 4 into your bore diameter square into your stroke length. We know that your stroke is 1.06 times of b. So substituting that, this expression is now in terms of b. So you can estimate the bore diameter. So it will becomes pi by 4 into 1.06 b cube. So b will be 8.97 centimeter. And using the relation, we can find out the stroke length as 1.06 times of 8.97, which comes out to be 9.5 centimeter. So your bore is 8.97 centimeter and your stroke length is 9.5 centimeter. Next is the average piston speed. So average speed is nothing but 2 times the stroke length into the speed. This 2 is there because it is 2 strokes per revolution. So 2 into your stroke length, so which is 9.5 centimeter, so 0.095 into your speed of engine, which is 3200, divided by 60 to convert it into per second, rpm to rps. So this comes out to be 10.13 meter per second. So any doubt in this question? I'll just make a change in this compression ratio. It will be Vd plus Vc by Vc. So I need a mistake here. So it will be Vd plus Vc by Vc. Compression will be total volume divided by the clearance volume. The total volume is displacement volume plus clearance volume. So that's how this comes. So moving on to the next question. A high performance 4-stroke SI engine has a swept volume of 875 centimeter cube and a compression ratio of 10.1. So the indicated efficiency is 55% of the corresponding ideal air standard Otto cycle. At 8000 rpm, the mechanical efficiency is 85% and the volumetric efficiency is 90%. The air fuel ratio, that is gravimetric, that is by mass, is 13:1 and the calorific value of the fuel is 44 megajoule per kg. The air is injected at 20 degrees Celsius and 1 bar. Calculate a specific fuel consumption in the Otto cycle efficiency of 60.2% and air mass flow rate, power output and brake mean effective pressure. we'll see how to solve this. So what all is given is you have a 4-stroke spark ignition engine which has a swept volume of 875 centimeter cube. So your displacement volume or swept volume is given as 875 centimeter cube. Then a compression ratio is given, which is 10:1, and also indicated efficiency is given, so 55. So indicated efficiency is nothing but indicated power divided by the heat which you are providing, so that is 55%. And then your speed is given as 8000 rpm. Also mechanical efficiency is given, so mechanical efficiency is again brake power divided by indicated power, and volumetric efficiency is also given, which is 90%. They are saying that R by fuel ratio is 13:1, and the calorific value of fuel is given 44 megajoule per kg. So you are saying air is injected at 20, so you have to find out specific fuel consumption when the total efficiency is 60%, cycle efficiency is 60%, and you need to find out mass flow rate of air, power output, and brake mean effective pressure. So we'll go by one. So we'll start with specific fuel consumption. The specific fuel consumption is nothing but 1 divided by your calorific value into overall efficiency. So your overall efficiency is mechanical efficiency into indicated thermal efficiency. So in the question it is given as indicated efficiency is 0.55% of ideal air standard or auto cycle efficiency. So auto cycle efficiency is 60.2%. So 55.55% of that. So 0.55 into 0.602 into 0.85, that will give you the overall efficiency, which comes out to be 0.281, and your calorific value is 44 megajoule per kg. So this comes out to be, the specific fuel consumption is 0.0809 kg per megajoule. So how did we get this specific fuel consumption? So if you see, efficiency is nothing but your brake power divided by brake, or else this is brake power divided by mass of fuel. How much amount of fuel is required for to generate 1 kilowatt of brake power? So that's what how you get. So overall efficiency will be brake power divided by m dot f into CV. So your m dot f divided by brake power will give you 1 by CV into overall efficiency. So how much of fuel is required to generate 1 kilowatt of brake power? So m dot f divided by brake power will give you SFC, or specific fuel consumption. So next is, you need to find out the mass flow rate. So the air mass flow rate can be found out using volume flow rate of air. So assuming an ideal gas, the air follows an ideal gas law. So P into V dot A into equals m dot A into RA T. So the gas constant for air is 287 joule per kg Kelvin, and your air can be written as swept volume. So the amount of air which is going in is swept volume into volumetric efficiency into the speed. So in this case, the intake stroke happens only once per 2 revolutions. So your speed will be n by 2. So your mass of air will be P into swept volume into volumetric efficiency into n by 2 divided by RA into T. So your pressure inlet is 1 bar and temperature is 20 degrees Celsius. So 1 bar is 10 power 5 Pascal into a swept volume is 875 centimeter cube. So into 10 power minus 6 to convert it into meter cube, and your volumetric efficiency is given as 0.9, 90%. So 0.9 into your speed is divided by 2. So 8000 rpm. So 8000 divided by 60 to convert it into rotations per second, divided by 2. So 8000 divided by 120 divided by the gas constant 287 into temperature 293. So 273 plus 20, 293. So this comes out to be air as 0.0624 kg per second. So that is the air requirement, mass of air requirement. So mass of fuel which is required will be mass of air divided by air fuel ratio. So brake power output will be mass of fuel divided by your specific fuel consumption. So mass of fuel we can find out, so it will come out to be 0.0624. So air fuel ratio is also given, which is 13:1. So m dot air divided by 13. And specific fuel consumption is 0.089. So 13 into 0.089, 0.0809. So into 10 power minus 6, it will come out to be 59.3 kilowatt. So that is the brake power output. So with that we can find out the brake mean effective pressure. So brake mean effective pressure is the brake power divided by swept volume into the speed. So this being 4 stroke will be again n by 2. So your brake power is 59.3 into 10 power 3 divided by 875 into 10 power minus 6 divided into 8000 divided by 120. So this comes out to be 10.2 bar. So next question is, a 6-cylinder 4-stroke automobile engine is being designed to produce 75 kilowatt at 2000 rpm with a brake specific fuel consumption. So previous was specific fuel consumption, so which is calculated based on, so this is specifically brake specific fuel consumption. So use brake power of 300 grams per kilowatt hour and brake mean effective pressure of 12 bar. So if it is given IFC, you have to use an indicated power. If it was BSFC, you use a brake power. So what is given is you have a 4-stroke automobile engine and it has 6 cylinders, and it is designed to produce a work of 75 kilowatt and speed of 2000 rpm, and the brake specific fuel consumption is 300 grams per kilowatt hour, and the brake mean effective pressure is 12 bar. So the engine is to have equal bore and stroke, so it's a square engine, so bore and strokes are equal, and fueled with gasoline with a heat of combustion of 44 510 kilojoule per kg. What should be the design displacement volume and bore? What is the mean piston speed at the design point? What is the fuel consumption per cycle per cylinder? What is the brake thermal efficiency? So we will see how to solve this. So engine displacement volume and bore. So your brake power is nothing but your mean effective pressure into displacement volume into speed. So from this rear engine we can find out displacement volume as brake power divided by mean effective pressure into speed. So speed is n by 2 in case of 4-stroke engine, because you are generating only one working stroke per 2 revolution. So speed is n by 2. So this equals your brake power is given as 75 kilowatt divided by mean effective pressure is 12 bar. So 1200 kilopascal into speed is 2000, so 2000 divided by 2 and divide by 60 to convert it into rotations per second, revolutions per second. So this comes out to be 3.75 into 10 power minus 3 in meter cube. or 3.75 liters. So that is the displacement volume. So from this we also know your bore and strokes are equal. So it's a square engine, so bore equals stroke. So this comes out to be displacement volume is pi by 4 into number of cylinders into d cube. So rearranging, it will become d is cube root of displacement volume into 4 divided by pi into number of cylinders. So displacement volume we know 3.75 into 10 power minus 3 meter cube divided by number of cylinders is 6. So this effectively comes out to be bore as 92.7 mm. Then your mean piston speed. So again similar expression, 2 into n into s. So 2 into your n is 2000 divided by 60 and s is 9.27 in 10 power minus 2 or 92.7 in 10 power minus 3. So that comes out to be 6.18 meter per second. So next is the cycle average fuel consumption rate per cylinder. So your mass of fuel is brake specific fuel consumption into brake power divided by number of cylinders. So the mass of fuel is 300 is the brake specific fuel consumption into the brake power 75 divided by number of cylinder is 6, and to convert into minutes we are dividing it by 60. So it gives you 62.5 grams per minute, because brake specific fuel consumption is given as 300 grams per kilowatt hour. So that we are multiplying by 60 to convert it into minutes. So it comes out to be 62.5 grams per minute, or so the average fuel consumption rate per cylinder is, so mass of fuel divided by the speed. So 62.5 divided by 2000 by 2, this comes out to be 6.25 into 10 power minus 2 grams. So that is the mass of fuel which is taken by each cylinder. So the brake thermal efficiency is, we know displacement volume. So the brake thermal efficiency is 1 by brake specific fuel consumption into your calorific value of the fuel. This is nothing but brake power divided by mass of fuel into calorific value. So just that. So brake specific fuel consumption is 300 grams per kilowatt hour. So we multiply by 1000. So divide by 1000 and multiply by divide by 3600. So it comes out to be 0.3 by 3600. So substituting brake specific fuel consumption. So it becomes efficiency is 3600 divided by 0.3 into 44510, which is the calorific value of fuel. So efficiency is 0.27. So brake thermal efficiency is 0.27. So moving on to next. A 4-stroke 2.5 liter direct injection automobile engine is tested on a dynamometer at a speed of 2500 rpm. So it produces a torque of 150 Newton meter, and its volumetric efficiency is measured to be 0.85. So what is the brake power and the mass airflow rate through the engine? So the inlet air pressure and temperature are 75 kilopascal and 40 degrees Celsius. So the engine power is so brake power is 2 pi into torque into speed. So torque into omega, so T into 2 pi n. So 2 pi into torque, which is given, produces 150, into speed is 2500 divided by 60 to convert into per second. So this comes out to be 39.3 kilowatt. So that is the brake power which is generated. So the inlet air density is rho is P by RT. So that comes out to be effectively 75,000 divided by 287 into 313. So that is assuming it's an ideal gas. So P equals rho RT. So P is given, inlet pressure is 75 kilopascal and your temperature is 40 degrees Celsius. So your density is 0.835 kg per meter cube. So mass airflow rate is half rho V eta V rho into Vd into N. So mass of air is half into 0.85 into 0.835 into 2.5 into 10 power minus 3 is the displacement volume into speed 2500 divided by 60. So it is 3.7 into 10 power minus 2 kg per second. So n is half here is because of n by 2. So your volumetric efficiency is nothing but mass of air divided by the theoretical mass of air. So which is the rho into swept volume. So next question is the Rolls-Royce CV12 turbocharged 4-stroke direct injection diesel engine has a displacement of 26.1 liters. So the engine has a maximum output of 900 kilowatt at 2300 rpm and is derated to 397.5 kilowatt at 1800 rpm for industrial use. So what is the brake mean effective pressure for each of these types? Second is the high performance version of the CV12 has a brake specific fuel consumption of 0.063 kg per megajoule at maximum power and a minimum brake specific fuel consumption of 0.057 kg per megajoule. Calculate the arbitrary overall efficiency for both conditions and the fuel flow rate at maximum power. So the calorific value of the fuel is 42 megajoule per kg. So we'll break down the problem. What is given is he has a Rolls-Royce engine which is CV12. So that says that you have 12 engines, 12 cylinders, and it is turbocharged 4-stroke. And the displacement is given as volume is given as 26.1 liters. So the engine has a maximum output of 900 kilowatt and the speed is 2300 rpm and it is derated, so it is operated at lower speed at 397.5 kilowatt and your speed is 1800 rpm. So what is the brake mean effective pressure of each of these for each of these types? So we'll see first part. So first brake power is brake mean effective pressure into swept volume into speed. So brake mean effective pressure is brake power divided by swept volume into speed, which is n by 2 for a 4-stroke engine. So for high performance engine, so when it is generating 900 kilowatt, so for that case your brake mean effective pressure is 900 into 10 power 3 divided by your swept volume is will be same 26.1 into 10 power minus 3 into your speed is corresponding to 900 kilowatt is 2300. So 2300 divided by 2 divided by 60. So that comes out to be 18 into 10 power 5. So that is 18 bar. Similarly for the industrial engine, so which is giving a derated to 397.5 kilowatt. So brake mean effective pressure will be 397.5 into 10 power 3 divided by your swept volume will be same 26.1 into 10 power minus 3. So into your speed is 1800 for this case. So divided by 120, this comes out to be 10.15 bar. So you see the mean effective pressure is lower. So specific fuel consumption for this case will be 1 by calorific value into the overall efficiency. So at maximum power, so your overall efficiency is 1 by 0.063 into 42 So calorific value is given as 42. So the second case, what is given is your break specific fuel consumption is 0.063 kg at the maximum power, and minimum is 0.057. So with this we can calculate the overall efficiency. So overall efficiency is 1 by calorific value into specific fuel consumption. So for the maximum power case, overall efficiency is 1 by your break specific fuel consumption corresponding to the maximum power output is 0.063. So and calorific value is 42 kg per megajoule. So this comes out to be 37.8%. So and the maximum economic condition is where the break specific fuel consumption is 0.057 and the calorific value is same. So this comes out to be 41.8%. So with finally calculating the maximum flow rate of fuel, which is brake power into specific fuel consumption. So this is corresponding to maximum power. So 900 into 10 power 3 into the corresponding brake specific fuel consumption comes out to be 0.0567 kg per second. So that is the mass of fuel. Before ending, I'll need to make a correction. So in one of the MCQ, the answer given was correct. So I'll give it expression. So if the intake air temperature is decreased, then the efficiency of engine will actually increase. So this is answer is correct. Why? Because so assume the air is intake runs an ideal gas. So when your temperature is lower, so for the given pressure your density will increase. So if your density increases much, you are taking in much more air, so your volumetric efficiency will increase. So as I told, volumetric efficiency is your mass of air divided by your density into specific volume, swept volume. So when your density increases, your volumetric efficiency increases, and so it leads to much more power which is getting generated. So intake air temperature being decreased will actually increase the efficiency of the engine. So that's it. With this I have finished what I prepared for today. So thank you, and next class we will see various process of internal combustion engines, so which we'll see in the next class. So with that note, I'll end this class. Thank you.